Sorry about that. We got cut off somehow, and I'm too far along to go back and re-record. But in any case, as you approach negative infinity, this right here goes closer and closer to 0. The angle whose tangent is 0 is 0 plus. As b approaches positive infinity, well, that grows without bound. Okay? And so you got to think, if something is growing without bound, where does arctangent have those vertical asymptotes? And that is going to occur at pi over 2. And then over here, arctangent of 1 is the angle whose tangent is 1 is again pi over 4. So pi over 4 minus a pi over 4, gone, gone. Minus 0 is nothing. This converges to pi over 2. So let a be a differentiable function with the properties that f of 5 is 7. It should probably be big F of 5. Let's change that to big F. And the limit as x approaches negative infinity of big F of x is negative 12. So what we want to do is we want to evaluate the integral from negative infinity to 5 of f of x dx. This is a cool way of asking about the fundamental theorem of calculus and about improper integrals. And so basically what we're going to do is I see we have the negative infinity and the lower limit of integration. So we have the limit as a approaches negative infinity of the integral from a to 5 of little f of x dx. And so I know from my fundamental theorem of calculus that this will be big F of 5 minus big F of a. Now the thing is, it's going to be the limit as a approaches negative infinity over here, and I didn't write that down, I should have. Limit as a approaches negative infinity of this expression. Okay, well, we know who the limit as a approaches negative infinity of f of 5 is. F of 5 is 7. And then we have minus f of a. Okay, we don't know who that is. But the limit as a approaches negative infinity of 7 minus the limit as a approaches negative infinity of f of a, that part comes from over here. Okay, I know it says x right there, but x is just a variable, as is a, so this expression is equal to negative 12. So the limit as a approaches negative infinity of 7 is 7, minus a negative 12, we're ending up with 19. And so infinite discontinuities. If f is continuous on the interval from a to b and has an infinite discontinuity at b, then what we're going to do is we're going to replace that upper limit of integration with some other number or some letter, and then we're going to let c approach b from the left-hand side. Now, I think this is easier to see if you actually see an example. And so what I'm talking about is something like this case right here, the integral from 0 to 1 of 1 over the cube root of x dx. Now, you'll notice that there's a discontinuity at 0, and this is what I'm talking about. Okay? So if it's the upper limit of integration, you're going to let c approach b from the left-hand side. If it's the lower limit of integration, you're going to let c approach a from the right-hand side. And then if f is continuous on the interval from a to b except for c and ab, at which there's an infinite discontinuity, then we're going to break up your integral at that value where it's discontinuous. Now, I think it's best to learn by doing. So we have the integral from 0 to 1 of 1 over the cube root of x dx. We're just going to rewrite this. Okay? Now, it's my lower limit of integration, so I'm going to let the limit as a approaches. And the way I think about this is I need to go down towards 0, and that's coming from the the right-hand side, excuse me. If you think about the interval from 0 to 1, you're going to be approaching 0 from the right-hand side. And so this is the integral from a to 1 of x raised to the negative 1/3 dx. Well, we're going to add 1 and divide. Limit as a approaches 0 from the right. Add 1, you're going to get 2/3. Divide by that, you get 3/2. X raised to the 2/3. And we're evaluating from a to 1. So this is the limit as a approaches 0 from the right of 3/2 times 1 raised to the 2/3 minus 3/2 times a raised to the 2/3. So this is equal to, limit as a approaches 0, 3/2 times 1 is just 3/2. And then the limit as a approaches 0 is 0. And so this converges to 3/2. Over here again, can't be plugging 0 into your denominator. So this is going to be the limit as a approaches 0 from the right-hand side of the integral from a to 2 of x to the negative 1/3 dx. So that's the limit. A approaches 0 from the right. Negative 1/2 x to the negative 2nd, evaluated from a to 2. Limit as a approaches 0 from the right. Now we're going to substitute, so this is going to be negative 1 over 2 times 2 squared. Minus a negative is going to be plus 1 over 2 times a squared. This right here is going to be negative 1/8 plus, now the only thing is, you substitute 0 here as you approach 0 from the right-hand side. Okay, this goes off to infinity, and so this diverges. And so where to split an improper integral? Here's another case, negative 1 to 2. You might say, oh, we're good to go there. But notice that we're discontinuous at 0. And 0 is inside this interval. So that's where we're going to split this up. We're going to say that this is the integral from negative 1 to 0 of dx over x to the 3rd. And then we're going to say plus the integral from 0 to 2 of dx over x to the 3rd. Now, before we keep on going, look at this integral. This should look, really, really familiar, especially since we just did that. Right over here, the integral from 0 to 2 of dx over x to the 3rd. That diverged. So over here, this is going to diverge. And since this diverges, the integral here will diverge as well. You only have to show that one diverges in order for this to diverge. Okay, another one. You might look at this and say, well, Mr. Chapman, we have 0 to 2, that's good to go, but if we substitute 1 here, okay, which is definitely in that integral, there's a discontinuity. In fact, this is actually a whole. So this is equal to the integral from 0 to 1. And I'm going to go ahead and factor that into x minus 1 times x squared plus x plus 1, difference of cubes. And then we're going to add that to the integral from 1 to 2 of x minus 1 times x squared plus x plus 1 all over x minus 1 dx. Reduces. Now there's still a hole there, so we're going to take the limit as x, in this case b, approaches 1 of x x squared plus x plus 1. We're going to add to that the, not integral, the limit as a approaches 1 of x squared plus x plus 1. I do need my integrals. What is going on with me today? Dx and integral from a, this is supposed to be a b right there, to 2 dx. My apologies. Okay, add 1 and divide. X to the third over 3 plus x squared over 2 plus x. Evaluated from 0 to b, and we're taking the limit as b approaches 1. I'm going to add to that the limit as a approaches 1 of x to the third over 3 plus x squared over 2 plus x. And that is going to be from a to 2. So here, substituting my b's, b cubed over 3 plus b squared over 2 plus b minus zeros plus the limit as a approaches 1, a cubed over 3 plus a squared over 2. I need to do my 2's first. 2 cubed, 2 squared, and then plus 2 minus a cubed over 3 plus a squared over 2 plus a. Now, this is going to be 1 cubed plus 1 squared plus 1. Then we're going to be subtracting 1 cubed plus 1 squared plus 1. So this and this reduce. And so this is equal to 8/3 plus 2 plus 2. 4 over 2 is 2. And so we got 8/3 plus 12/3, which is 20/3.